So this video will be an overview of measurements in science, rounding, so how we round our measurements, and then also what we call significant figures or sig figs. So anytime I say sig figs, I'm referring to significant figures. So now there's a few very common measurements that we're going to be using quite often. So in terms of length, most commonly we might use centimeters. So cm is the centimeter. So the base unit of that is the meter. And a meter is roughly about the same length as a yard. They're slightly different. The centi part is actually, it means 10 to the negative 2. So what that really means is that, and I'll explain this in another video, but 100 centimeters comprises 1 meter. And then we will just use lowercase m for meter. Centimeter is cm. There's also little m, and this is for millimeter, where milli is 10 to the negative 3, where that means there's 1,000 centimeters in 1 meter. Now for mass, we will commonly use the gram, which is abbreviated with a lowercase g, and then we'll also use kilogram, which is kg, and then the kilo part is 10 to the third. So that tells us that there's 1,000 grams in 1 kilogram. These are the two most common mass measurements that we'll use, grams in particular. We could use milligrams, where the lowercase m in front is the milli, and again, milli is 10 to the negative 3. So that would tell us that there's 1,000 milligrams in 1 gram. We might use that one as well. And then for volume, the most common measurement that we will use is the milliliter. So we have capital L for liter and lowercase m for milli. And again, milli is 10 to the negative third. So that means that there's going to be 1,000 milliliters in 1 liter. And then of course you might use the base unit, which would just be capital L for liter. But those are the most common measurements that we will use. In another video, I'll have the metric system outlined so you can see what all of these, centi, milli, and kilo, how they stack up. So the next thing on rounding, so just kind of I'm not sure if you're familiar with the rules of rounding already, but just to review, the general rule is that if we have a number, like say it's 10.49, and we wanted to round that to the tenths place, we look at the digit that comes right after it, and generally if it's 5 or higher, we would round up, and if it's 4 or 0, we round down. So 10.49 rounded to the tenths place would turn into 10.5. If this was 10.44 and we wanted to round it to the tenths place, we look at the 4 and we round it down to 10.4. A couple more examples. Let's say we had 100.123 and we wanted to round it to the hundredths place. So to this location, we would look at that 3. That 3 is less than 5, so we'd round down to 100.12. And if we had 100.127 and we wanted to round it to the hundredths place, we'd look at the 7. It's greater than 5, so 100.13. And then one last example, let's say we had 0.055 and we wanted to round this to the hundredths place. If it is 5, that means it's going to round up. So we'd round this to 0.06. So then the last part of this video, I'm trying to make all these videos nice and short, significant figures, so sig figs. Now sig figs are important because when we have equipment in the laboratory, some laboratory equipment is more precise than others. So one piece of glassware that you might use in the laboratory is like a beaker, and we don't have a picture of it here, but beakers are generally imprecise. They're useful for just measuring out rough amounts of liquid. Some more precise measurements or more precise pieces of glassware are like you see in the photo here. So a graduated cylinder, for example, all of these little markings that you see on the graduated cylinder, that's basically like the level of precision. So the more markings you see, the more precise that piece of equipment is. Syringes can also be very precise depending on, again, how many markings we see. Burettes are known to be extremely precise. So it's usually every 1/10 of a milliliter or so. A pipette can be very precise. Sometimes they might have only one marking up here. Sometimes they might have just a few. It kind of depends on the pipette. And then volumetric flask. The interesting thing about a volumetric flask is it's very, very precise, but only for a single measurement. So this might be a 100 milliliter volumetric flask. And you know you have 100 milliliters to many digits or more digits than these other pieces, only if the water level is right there at that line. Another example for mass balances. So this example from the book, this is a triple beam balance. So this one might only go out to the 10th place, so to a precision of 0.1 grams. But then this one, this kind of, it's another type of triple beam balance, but this one might go to 0.1 grams, so go out to the 100th place. This is the kind that we have in our laboratory that you more commonly would see, but this is the most precise, and you can see from the little drawing, it goes out to 0.001 grams. So we would say that this one, the electronic balance, has, it's basically like the most precise one. So we get more significant figures when we use one like that. Now, to actually go over the rules, I've got a bunch of examples we're going to do, but here are the rules of significant figures, and they are in the book. So we've got a couple rules. So this is on page 15 in the book, but I'm just going to outline the rules. So rule number 1, non-zero digits always count. So if you have a 1, 2, 3, 4, 5, 6, 7, 8, 9, those are always going to count. The rest of the rules address zeros because that's what usually gets students caught up. So the next rule, a 0 in the middle, someone that's been sandwiched, so to speak, does count. So I'll say zeros in the middle of non-zero digits, they count. And I'll demonstrate that with the examples that we're going to do. Rule number 3, placeholder zeros do not count. And a placeholder 0 is usually a 0 that just gives you an indication of how large or how small that quantity actually is. And they need to be there so that we all know how large or small it is, but they don't count for significant figures because they don't actually contribute to the precision of the measurement. And then the last rule, zeros after the decimal, after non-zero digits count. Zeros after the decimal and after the non-zero digits. Those count for sig figs. So to illustrate these rules, I'm going to go through a whole bunch of examples for you. So first example, 2 grams. We've got one non-zero digit. So this one counts. So this is 1 sig fig. So I'll write SF just to abbreviate sig figs. We have an abbreviation on top of an abbreviation. But just 2 grams, just 1 sig fig. Next one, we've got 2.0 grams. So we have a non-zero digit and then a 0 after the decimal that's after a non-zero digit. So both of these count. So this has 2 sig figs. Next example, 2.00. We have a non-zero digit. And then these zeros also count because, again, they're after the decimal after a non-zero, so this is 3 sig figs. Next one, 1.06 grams. So we have non-zero digits, and then this zero in the middle, this one's being sandwiched. So that was the rule number 2. So it's going to count as well. So this one has 3 sig figs. Next example, 1.70 milliliters. So the non-zero digits count, and this is a zero that's after the decimal, after a non-zero, so we have 3 sig figs. Next one, 1,030 milliliters. So the 1 and the 3 count. This zero counts because it's being sandwiched, but this zero over here, this one actually does not count. That's what we call a placeholder zero. It's just telling us that we have something close to 1,000 milliliters instead of only 100 milliliters. So with this example, we're only going to have 3 sig figs. Next example, 1,000 centimeters. So the 1 counts, but these 3 zeros here do not count. Again, those are placeholder zeros. They're just telling us that we have 1,000 centimeters and not 1,000,000 or only 10. So this only has 1 sig fig. Next one, 1,050. So the 1 counts, this sandwiched 0 counts, the 5 counts, but this 0 on the end does not count. So this is 3 sig figs. Next one, 400,500 meters. So the 4 counts, the 5 counts, and then these zeros that have been sandwiched count, but these 2 zeros do not count. So this is 4 sig figs. Next example, the 4, the 5, and the 8 count. This 0 that has been sandwiched counts. It's a 0 in the middle, rule number 2. And then these zeros here also count because they're after the decimal. They're after the decimal and after the non-zero digits that appeared. So here we have 6 sig figs. Next example, 478.960 grams. All of these are going to count. So non-zero digits, and then this 0 that is after the decimal and after the non-zeros. So this one has 6 sig figs. Next one, 270 kilograms. The 2 counts, the 7 counts, but this 0 here does not count. There's no decimal. It's just a placeholder 0 to tell us how large a number we have. So this is 2 sig figs. Next one. Okay, now we're talking about numbers less than 1, 0.0050. So the 5 counts, and here's another number, another 0 that's after the decimal and after the digits, but then these zeros do not count. Those are placeholder zeros. These zeros are telling us how small of a number we have. These zeros are telling us that we have quite less than 1 gram, not 50 grams or 5 grams. So this example has only 2 sig figs. Next example, we've got the 8, the 2, a sandwich 0, and then these are placeholder zeros, so these are not going to count. So this one has 3 sig figs. Next example, the 7 counts, but then all of these other zeros, these are all placeholders. These are all just telling us that we have a very, very tiny number, not 7 grams or 70 grams or 7,000 grams. So this is only 1 sig fig. So now this one, we've got a lot of sandwich zeros here. The 1 counts and the 5 counts, and then we've got 3 zeros being sandwiched, and then we have another 0 that's after the decimal, after non-zeros. So this has 6 sig figs. This one we've got a 1, a 5, and a 7, a sandwich 0, and then this 0 is appearing after the decimal, so that one also counts. 5 sig figs. This one, 1,000 kilograms with added precision, so that 1 counts. And now this one's interesting. These zeros are appearing after the decimal and after a non-zero digit. Here's our non-zero digit, the 1, which means that these zeros are now being sandwiched. So they're all going to count. So this has 6 sig figs. Now there's one more rule about significant figures that I'm going to mention that's a little bit, doesn't come up too often, but if you are counting something, so the book has a picture example where it's like counting the number of quarters you have. Another example might be counting the number of students in a room. But anytime you're counting something where you can't have half of an object, those are going to be exact numbers. So we might say like infinite number of sig figs. So counted quantities. So for example, 8 quarters or 10 students. Basically, like it's almost like the sig fig rules don't apply, but quite often you might see it written as infinite sig figs. Basically, you don't have to worry about how many sig figs those quantities have when you're trying to figure out how many sig figs your final answer should have. And when we do the sig fig operations video, we'll explain how we figure out how many sig figs our final answer should have. Now, this infinite sig figs idea also applies to definitions. So we had some definitions up above. For example, there's 100 centimeters in a meter. That's like a definition. The sig fig rules are not going to apply here either because we're counting. It's exactly 100 centimeters makes 1 meter. That's how we define the centimeter. And same thing here, 1,000 grams makes 1 kilogram. That's a definition. Another definition might be 12 inches in 1 foot. We've all agreed that it's We've all agreed that it's exactly 12 inches in a foot. So that would be another definition. Anyway, that's our first video on measurements, rounding, and significant figures.